silence for those who have lost their lives in accidents that they were not related to in our suit. Gaza and Syria. Thank you. Ladies and gentlemen, esteemed professors, fellow colleagues, we would like to welcome you to our second presentation of our thesis topic. I'm going to introduce myself, Yasser Sour, Karim Dayhoum, Ahmed Sultan, Salma Behey, and Ali Seif, and we are rubberized concrete. Our outline will follow our previous presentation in similar fashion. First off, we're going to present a quick recap of our topic and why we found it important to pursue this topic, and further cement that notion in our objectives and scope section. Then we're going to show our tests and the tests we concluded in our experimental work, and our sample of results section will show you the observations that we have seen and the results from which we have attained. Then we're going to discuss the obstacles in which we faced and surpassed, and take a look into the future in our anticipated outcomes sections. In the end, we're going to look at our timetable, see where we stand, and make sure we're in progress. Okay. An American juror once said that the great thing about humanity is not where we stand, but in which direction we are moving. In which direction are we moving? We are seeing great successes in the field of engineering. We are seeing engineering marvels being built in places like Kuala Lumpur and Dubai. But at what cost? The Earth is running out of its natural resources, and much like fossil fuels, coarse aggregates are one of them. We believe coarse aggregate is being proved extremely difficult to find consistent, good quality coarse aggregates in our market for our projects. We believe that the solution lies in rubber, specifically rubber tires, waste rubber tires, because rubber tires are found in abundance all over the world and are being produced at an increasingly frightening rate. Moreover, we've seen rubber implement great successes all over the world in various engineering applications. We are enthusiastic that we can replicate that same success in the construction engineering industry. We would also like to point out Marceau. Marceau are the company that helped us shred our tires for our experiments. They were founded in 1970 with the noble goal of taking recycled rubber and turning them into useful materials, such as floor mats for our cars. In a nutshell, our objective is to explore the feasibility and flexibility of partially replacing coarse aggregates with similar sized rubber, and to what extent we can implement it in our construction methods. We've done our research, we've been through a rigorous literature review, and we hope that our experiments can prove us right.
Okay, so I'll be explaining the experimental work to you. This is just a basic outline of the mixes. We were using six mixes, and we will still be also continuing to use this mix until the end of our feasibility study. We have the control mix, which is the conventional mix, and then the 10% rubber untreated, 20% rubber untreated, 30% rubber untreated, and then we also use two different treatments, which are cement paste and silica fume, for the 20% rubber. The procedures. Unfortunately, the rubber that we were using was not according to the size that we expected. We were expecting a certain specific size, and the batch of supplies that we received came at different sizes. As a result, we had to conduct the process of sieving, and this was done through the mechanical sieving machine and the manual sieves. We've also conducted, as I explained before, the treatments, which were the cement paste treatment and the silica fume. And basically, what we were using for the cement paste was that we'd ensured that having obtained the rubber, we'd first sieve it through either the mechanical sieving machine or the manual sieve. And once we've completed that process, we'd wash the rubber, and then leave it to soak, leave it to drain out the water, and then immerse it in cement paste. This is for the first treatment. And then for another treatment was the silica fume, where we'd also immerse it until we'd ensure that the rubber has been covered in the silica fume. For the cement paste, we were not able to use once we covered the rubber in cement paste, we were not able to use it immediately. We had to wait for a period of 24 hours. Whereas with this treatment for the silica fume, we used it immediately once the silica fume completely covered the rubber. So these are the total number of tests that we've conducted. We've just outlined it and organized it in 3 different bubbles, as you can see. We have the physical properties of the rubber and the tests along with it, and then we have the hardened concrete testing with their specific tests, and then the fresh concrete testing, and we'll be going through each and every test. Okay, so from the absorption that we've conducted on the rubber, we were able to obtain a value of 1.92%. And according to the research, for the value of absorption for the conventional coarse aggregate, this was found to be a value within the range. For the unit weight, you can see the vast difference between the 1.2 and the 2.6, and this just shows you how much by using the rubber it will lead to a reduction in the weight of the concrete. Then for the gradation, as I mentioned, because of the different sizes of rubber that we received, we had to conduct the process of sieving, and so to make sure the size that we used for each and every experiment was consistent, we were running it through the sieve and making sure it passed sieve number 38, whilst also being retained on sieve number 4.
Okay, so as for the fresh concrete testing, you can observe that our mix design gives us a relatively low value for the slump. As you can see, the conventional give us 1.5 centimeters, while 10% rubber give us 1 centimeter as a slump value. Also, we have conducted an air content test on different occasions, on different mixes, and its average came within the range of 1 to 2.7%. Which by its place come within the range of normally used conventional concrete. Last but not least, the unit weight, which was conducted on both conventional and 10% rubber, and was found to be 2,400 and 2,200 kg per meter cubed, respectively. So moving on for our hardened concrete testing, and as you can see, our compressive strengths had greatly been affected when introducing the rubber particles inside, so meaning that after 28 days the conventional achieved as high as 47 megapascal compared to 25 megapascal for the 10% rubber, with approximately a 47% decrease. Also, I want to highlight that this decline was somehow anticipated according to our literature review and research. But we've also known that introducing rubber particles inside the concrete could add or improve new properties or improve its original properties in return to its reduction in strength. Okay, as for the flexure strength and deflection tests, we've only conducted them on the conventional 10%, and you can see that the 10% has a slightly higher stress of a difference of 0.6 megapascal. This can be shown and can be noticed even more in the deflection values that we obtained. The conventional get us an 0.6 millimeters, while the 10% rubber given 1.5 millimeters respectively. This is a quick video that I showed for both specimens, showing the failure of conventional 10%.
Double click.
Yeah, as you can see, this is the convention one. Its failure was completely brutal. You will observe here the failure of 10%, as you can see, going to like a ductile failure.
In order to get a better understanding to our topic and the replacement of rubber to put aggregate, we are going to know the relationship between stress and strain to our new concrete and its behavior according to different load involvement. And since the MTS, the material testing system, can only apply load to the maximum of 400 kilonewtons, we have taken, as you can see in this picture, the LVDT from the structure lab. We connected it to our compressive strength machine, and then we took our specimens, our cube, and conducted the test on it to give us a deflection versus load relation. And here, as you can see, if we get to compare our specimens to get a comparison between the conventional and the 10% replacement of rubber, you can see that, for example, at 400 kilonewtons at the conventional sample, it will give us a deflection of around 1.7 millimeters, whereas it will give us at 10% replacement around 2.3 millimeters deflection. This indicates that this might be a reason of the higher deflection might be a reason of the replacement of the rubber, since it gives us more flexibility, as you have seen in the previous video. Another concern we have for our idea was the reaction of our specimens towards a consistent temperature change, and accordingly we have thought to have the elevated temperature test. The procedures of the test were basically taking our specimens, putting them into the oven, and taking how their ability to resist any forces would change. At first, our specimens were, as you can see, were here in the oven. Our specimens were 2 cubes and 2 beams for each mix. We took them, put them in the oven at 200 degrees Celsius for 4 hours, and then we weighed them before and after putting them in the oven. And here, as you can see, as the percentage increases of the rubber inside our mix, it gives us higher weight loss, higher percentage weight loss for the sample. We have investigated and thought it might be due to the melting of the rubber inside the mix due to the high temperature it is exposed to. In addition, it might, but in both, it might be this weight loss, this high weight loss, might be because of the evaporation of the water inside our mix. Then, after we took our specimens out of the oven, we also took them to test them for different loading enforcement, and as you can see in the result, in the graph, the addition of rubber inside our mix increased its ability to resist loads, whether at a beam, at the compressive force, or the fractional force, or compressive for the cube, or fractional for the beam. And what we have also thought of, it might be due to the loss of mechanical property, which we have observed when we took a look at our specimens, when we got them out of the oven, that here, as you can see, the 10% rubber mix had some cracks before testing it, while the conventional was taken out, seeing as we took it in. As for the impact test, we have thought to conduct this test since the rubber has an ability to absorb some energy. So we thought that it would give us higher impact resistance. And due to our time plan, the time was not became to test these specimens. However, we have done with almost touring all the beams. And here, as you can see, we had to do special formwork for the beam, since the machine takes a specific size for testing the input. This is our formworks, and we have the testers for reinforced beams, as you can see. These are our beams. This is the pouring process, and this is our machine where we test our beams for impact resistance. Last but not least is our abrasion test. We faced some difficulties in testing abrasion since the machine was not working. However, we were done with finishing our specimen and waiting for the 28 days to pass to test them. This is our conventional sample without rubber, and this is our 10% sample with 10% rubber. The specimen is 2 inch by 2 inch by 2 centimeters, and this is a picture of us ensuring that the machine was fixed, and that when the time comes at 28 days pass, that we can safely use the machine and get our tests done. And another test we're still conducting is the thermal conductivity. We're still getting the permits to get there and do it for our tests complete.
Okay, while conducting our experimental works, we faced some obstacles. One of our major obstacles was conducting an efficient time schedule to conduct our experimental work, given that there are other groups using the labs at the same time. Another obstacle was acquiring the shredded rubber. It's not only acquiring the shredded rubber, but a consistent supply in the shredded rubber. Beginning the initial phases of experimental work, we still didn't get a grasp on how the procedures work. We started mixing and we faced some complications, and these complications were then fixed by changing the mix design, making modifications to it, and the experimental process and procedures also. Okay, what we need to get out of this study by the end of the semester is we need to have a complete understanding of the rubber, concrete characteristics and properties as opposed to the conventional concrete. Therefore, finding an application for its use in the construction industry, given that we have by then identified some pros and cons in the material, it would aid us in doing so. In doing so. Also, and some outcomes is we work as a team in adapting to different and various unexpected circumstances like the strike and other stuff like that. Okay, our progress update. We stand on presentation 2. As you can see, we still have some experimental work and results and analysis to conduct here to be able to give a conclusion. And we hope by presentation 3 that rubber concrete would have lived up to our expectations, and our thesis study would live up to yours. Thank you.
You should have expected that the strength will be less when you use rubber and the concrete. What are you going to use the rubber concrete for?
Because of its energy absorption nature, we suspect that it's going to be better in resisting some impact tests. Therefore, you can use it in many applications that require the concrete to be better in impact.
In other words, foundations for machines, railway track, highway pavements, and so on, right?
Ship
so
decks.
Your testing should be in that direction. I mean, you're talking about abrasion resistance. I mean, what do you do that for? How are we going to express the energy absorption or the mechanical energy absorption by the concrete?
Okay, we don't know that we're waiting for the 28 days to pass for the impact specimens.
The impact specimen will not show you how much energy that concrete can absorb. You do that by stress strain curve, stress strain test. And I noticed that you mentioned that in the beginning. I was very excited. I said, wow, these people are going in the right direction. And suddenly, I didn't find it. And I found out that you're running the load deflection test on a cube. Although we know that the cube is not a proper specimen for stress strain curve.
We'll be producing the stress strain curve by the end of the semester, after we get all the load deflection curve for all the samples. So we'll be able to get and produce the stress strain curve
How?
for every
Have you poured the samples yet?
Yeah.
What samples?
Beams.
Sorry?
Beams.
No, that's not the stress strain curve. You do that for a cylindrical sample. And that's your target, that's your job. Because that's what is going to measure the mechanical energy absorption in the specimens. Anything else be, kind of a side product. One last thing before we leave this. I hope you're not going to hold the specimen by your hand when you run the abrasion test. Because the picture is showing that. So that's not right.
Yes, it was not
Sorry.
working, and they told us there is something that fixes the specimen, and then now this is the process.
But the solution is not to hold the sample with your hand.
Yes, we're expecting them to fix it.
Oh, okay.
This was only a trial.
This was just a trial.
Fine. Thank you.
Could you please sum up the advantages of the rubber concrete over the conventional one? Because actually I saw in many of your slides that maybe the conventional one is better.
Our feasibility study isn't proving whether the conventional is better than the rubber. We're just looking to see whether actually, removing some of the coarse aggregates and putting in the rubber, what it would give. We don't have an exact, we're just looking at whether we want to see the results and compare and just see if it's either feasible or not. Because that's the question we're trying to answer.
What did you think about rubber?
Because rubber has an environmental, rubber unfortunately in Egypt and all over the world, rubber tires are thrown away and sometimes they're burned and they have an effect, a very negative effect on pollution, and so we thought instead of throwing that rubber away, why not use it in something that can also be beneficial to the construction industry?
Position, we also thought of that because we have recognized the safety of good quality aggregates, so we were thinking to get another replacement for the good aggregates that would maybe give the same effect.
Not necessarily use the rubber concrete for structure elements, maybe for other elements or other applications.
Actually, I'll go back to a discussion that was raised earlier. Can you go to the slide that shows the compressive strength of the, not after heat, the one that shows the reduction of both? Now, what is the compressive strength you're getting with 10% rubber here?
Almost 25
Huh?
approximately 25 up to 20%.
So with the rubber, you still get some fair strength. I wouldn't call that high or anything like that, but some fair strength. So you cannot exclude completely the possibility this can be used in some applications. It doesn't have to be highly structured or other. So yes, there is a reduction, but don't you agree that there is still some good strength being obtained here?
Yes, if we think to use it as a lightweight concrete, it might give strength that is comparable to lightweight.
Something you didn't show a sample of the results for, and maybe you save it for the end, but I don't know. But could we raise this 25 a little bit if we really after compressive strength, although that's not everything?
That's why we use the treatments, because
You did mention that, yeah?
through our literature review, we have tabled that both our treatments, they enhance the bonding and accordingly they enhance the compressive strength. And that's what
Do you finish these results in the lab?
some of them, not all of them.
Does it look like this could be the case?
Yes, and we have tested some of the compressive strength treated samples, and they showed it would.
And so my point is, without any treatment, you still have some fair strength. I would use the word fair. And even that fair strength, if you don't like it, you still could use the other things that you have to raise even further. One comment is that I think you have made some kind of training on the MPS machine, correct? I think that's a useful information. If even 7 or 14 days specimens on the MPS would be used.
We did, but the thing is that we needed to test it on samples that can resist more than 200 kilonewtons, and that's why we thought of getting the LVDT and
Please could use smaller samples that could be affected by that to capture some of the data for the stress thing.
I have actually one comment about the consistency of the property of rubber. I mean, after 1 or 3 years, will it be with the same behavior? I mean, the rubber is might dry somehow. I mean, it might not give the same properties. Is this a possibility in our case or not?
I mean, it's a possibility, but basically rubbers as coarse aggregates are covered with like a concrete cover. The only thing that happened here, in elevated temperature affected it negatively or greatly. In this case, we'll be using other materials to protect it from elevated temperature or any other things that negatively affect it.
During the lifetime of any structured element constructed with this type of concrete, I mean, it will be subjected to heating and cooling with time. I mean, shall it be an effect on the property of the concrete itself?
Yeah, add to that. Rubber is, in essence, a non-biodegradable material, which poses a huge problem for environmentalists because you can't easily get rid of rubber. It can't be decayed. It just stays there. So placing it in a concrete mix, we're not sure, but we don't think it's going to decay any of its properties, because its properties so far are proving to be, they're not exactly, but they're partially similar to coarse aggregates properties. We might do further tests to examine that notion, but we've already did the elevated temperature test with positive results. We hope we get better results in the future.
Anyone?
Yes, you indicated that you would be testing 10, 20, and 30%, but I only see the results of the 10%.
Okay. We have poured almost all of our specimens, but because we're like halfway mid through the semester, our testing is still in progress. Some tests have been done and some haven't, so you couldn't compare all the properties in one. Like we've already been done with the conventional at 10%, and some of the 20% are in, and some are being tested in progress. So for the sake of this presentation, we thought to just give you 2 examples, and on our final conclusion, you're going to see it.
The mix is cement, sand, and rubber?
No, and coarse.
And coarse, it's only partial.
And coarse
Yeah,
aggregates. So what does the 10% mean?
We
So we remove 10% from the coarse aggregates and replace it with the same amount of rubber.
Do you think we will just hide the unwanted rubber in such large quantities so that we get into the hassle of transporting them to site, making them that they are homogeneous? And then what, per cubic meter of concrete, what do you think, how much liters of rubber could probably use in 1 cubic meter of plain concrete?
For 1 cubic meter, approximately.
It depends on the percentage we're getting, but here we have all the amount of rubber used, the mix design, the whole mix design. So we have a rough vision of how much we're using in 1 meter.
Did you observe the development of hair tracks once you handled the the concrete with rubber. I mean, if you want to benefit from its resistance to impact, then you definitely will develop air cracks into these very skin, I mean, whatever is covering the rubber. So you cannot benefit from that deformable material if it is hidden inside unless you somehow nearly crush the surface layers. What is reported and what are your observations to this?
No, we don't get anything about crushing the surface.
I mean,
of the
rubber, yes, it is deformable, but it's not on the surface. It is inside. So,
the whole structure through the impact test. If it resists more impact during
but you will benefit from the rubber once cracks will start to develop, and then you get part of the load transmitted to the rubber. So, I mean, you already did. If you notice that when you tested the beam was not broken in the middle. It was broken on one side.
But it's in the middle third of the beam. According to the STM.
Well, it looks like that beam was, the material was not very homogeneous.
That doesn't mean that it's not very homogeneous.
Does not mean?
No, not necessarily.
Where is the maximum moment?
Where is the maximum?
It is the middle.
According to the STM, the failure could happen in the middle third of the beam. So it happens in the middle third, so we could accept this specimen. So.
الماكسيموم في الميدل طبعا في الشريط بس يعني not necessarily البريك بيحصل بالظبط في الميدل as long as انها in the middle 1/3 يبقى acceptable test. طبعا هتقول في شويه inconsistency.
This is the weak section.
يعني في inconsistency طبعا يعني مش معقول هتبقى no matter what.
What is the cost of a cubic meter of rubber?
I think the 1 kilogram is 3.5 pounds.
So, cubic meter will cost how much?
Now, because the recycling market in Egypt has not yet developed that well. When you have demand on the market, like the competition in the market, they can lower the prices and stuff. But when you find 2 or 3 companies that do this, then they're gonna have a higher price. That's it. And that's the observation we had.
Thank you. Thank you very much. Thank you.